But let's go ahead and start. So we're going to talk first of all about number system and codes. So what are number systems? What do y'all think?
Way to label stuff?
It's a way to label stuff. It's very pretty good. Yeah, pretty much. So how many of you have taken analog versus digital and know the difference? First of all, what is analog? Let's start off with that question right there. What is analog?
It can be adjusted. Right? Through the wavelength and the. I can't think of it. Rich told us this in another class.
Okay, so you are on the right track. So go ahead.
Isn't it just the signal on and off?
No, that's digital. Digital's true or false.
Analog, think of analog like a light switch that has a dimmer on it. You know what I'm talking about? So if you have a light switch with a dimmer, go ahead.
Or how you adjust the radio signal.
Exactly. That's analog. Digital is either on or off. So if you have, it goes back to that light switch. There's one type of light switch where you can choose the level of light you want versus your basic light switch, which either turns the lights on or off. There is no in between. Does that make sense? Okay. So you might want to make sure you recognize that, because that's typically a very good test question, is the difference between analog and digital is analog can have a variety of signals, a variety of readings, a variety of something. It has a range of, how to say this? It has a range of everything. That's analog. Digital is either yes or no. There is no in between. Does that make sense to everybody? All right, so what is a numbering system?
A system that is based off of numbers and algorithms.
Very much. All right, so I kind of gave you the answer with this one, and that's the base of numbering systems can be in decimal, which is our typical one we use on a day-to-day basis. Binary is what computers use. You have octal and you have hexadecimal, which again are in computer terms. That's more electronics and computer user friendly. So how many of you have heard the words bit, nibble, byte, and word?
We use space size.
I've heard it.
Okay, we'll get into a little bit of it, but terabyte. That should be right. That right there should be the biggest clue in on this. Excuse me.
1,000 gigabytes.
Yep. So this all ties together to each other, and we'll kind of dig deep into it. So digital versus analog. Digital is something that varies in steps. It's only one or two, yes or no, true or false. We've kind of said that a few times now. Analog is something that varies. So temperature is something that varies. Pressure is something that varies. Velocity varies. Those are some of the biggest things. Light levels can vary. Things like that, right? So with analog, so this guy is analog. So he has a smooth and continuous change to keep him running. Versus digital, which either it's on or it's off. It's yes or no. There's no in between. Y'all see that? So you have a digital watch. This is the output signal you would see. You have an analog watch. Those are the old-time regular watches, for those of you that don't know what an analog watch is. All that has is the battery and things that spin around and gears and such, and this is just kind of how it runs itself. So you have what are called digital representations of analog quantities. This is how you get things like CDs to work. So let me ask y'all this. How many of y'all know how a CD or a vinyl record actually work?
CD uses laser, and I think a record uses grooves inside of its material.
Okay, so you're very close. Technically, a CD does as well. How to say this? My brain's trying to go 1,000 miles an hour, and I'm trying to make sure it doesn't. Okay, so let's see. Okay, so if you ever look closely at a CD, I was going to try and draw something for y'all, but this thing won't let me have a pen. So let's say you have a CD, okay? If you ever looked really closely at the CD, just like on a record, you'd see bumps and divots in that encasing. That's how it's encoded. That's why you can't change a CD programming. Does that make sense so far? So let me kind of see if I can draw it out here on this whiteboard.
So vinyl would be an analog recording, and CDs and DVDs would be like a digital.
Okay, so for both digital and for both CDs and vinyls, so this is, we'll call this a CD or a vinyl, whichever way you want to do it. What you don't see are microscopic. You should see this whenever you look at a CD at an angle, the rainbow side. You see how, I don't know how many of you actually have looked at a CD lately, but they have those concentric rings to them. Y'all know what I mean?
Yeah.
Okay. So let's see real quick. Okay, so here we go. Let me pull this over here just so y'all. Okay. Let's bring this over. Okay, so if you've ever really looked closely at a CD, okay, so you have to tilt it certain ways, but you can see little lines that run all the way out here. If you've ever seen a vinyl disc, the ones that you put on a record player or something, they're the same way. Okay? So that's why I said they're both pretty much analog devices, because those bumps and divots are what allow it to play and be able to carry all that different music. We are able to encode. Sorry guys, this thing's being a goober real quick. So the way that we encode this is what allows us to play the music. However, CDs, are they reusable as a memory device? Are CDs able to be reused after you've already written them? Anybody?
Yes.
Actually, not really. Once you've written a CD, and I don't know if y'all know what I mean, but once you've put it in your machine and you've told it you want to save it to that CD, a little laser comes in and etches that information into the CD. That's why it's really bad to get dust and stuff on a CD, is because that interferes with the etching, A, or B, it scratches the surface, which just like if you have a scratch on a vinyl record, what happens?
It's
It becomes useless. You can't hear anything because it'll hit that scratch every time. Same thing for a CD. Once you've etched it, once you've set it, it cannot be changed to something different afterwards. It's there for life.
Is that why they say that you burn a CD?
Yes, I believe that is why it's called burning a CD. Because once you've set it, it can't be changed. If you do, you corrupt the data completely that's on it, and it becomes a useless piece of crap. It's probably the gentlest way I can say that. That's why CDs never became the big memory devices that people thought they would. Something like a floppy disk can be erased. Something like a hard drive can be erased. Something like a flash drive can be erased. CDs, can't do anything with them. They're great for media that you want to store permanently. They're not so good when it comes to being able to rework or rewrite over that disk. Does that make sense to everybody?
Yeah.
So, that's why it's a digital representation of an analog quantity. We call it digital because just like with a record player, the needle moves or the laser moves as it reads the disc, which allows the sound to become a digital representation of it. But it is a technically analog device whenever you are using it. So we have things that convert digital to analog, digital signals to analog signals, as well as analog to digital. Okay? Does that all make sense, guys?
Yes, ma'am.
Okay. Analog to digital converts. You have single bit, you have flash players, successive approximation. You have integrating circuits. You have all sorts of different circuits that allow you to convert analog to digital. Why? Because digital, for all the fact that it's nothing but ones and zeros, is how most of our world is run. Okay? Digital is how most of the world runs. Versus converting digital to analog. That means we got to go a step back. So here's our digital representation. So what they do is here's your analog signal. So let's say somebody is singing and they're singing to create your CD. And how do we get that CD to go to the amplifier? Right? So we have an analog signal because anytime you sing or anytime you do things like that, you create an analog signal. So I don't know how many of y'all sing or you listen to music, but you should have kind of pick up on this is the fact that when somebody sings, it's not one note and then they stop. They modulate their voices a lot, which means that your signal has to accommodate that. So what they're able to do is at certain places, they give the analog signal a digital value. Does that make sense? So they convert it from analog to digital, which digital goes to the CD. Then it converts from digital to analog, which allows it to go to the amplifier. Any questions so far, guys?
So is it kind of like a transistor?
Yes, kinda.
Oh, okay.
Basically, you're moving things between digital and analog signals to be able to compensate for the fact that there's not always a direct link between the two. We no longer have somebody that comes and sings to us over the radio. We have things that are recorded so that they don't have to. Not like back in our parents' times when everything was live studio, live everything, right?
So like back in like I say the disco days when they had the big old DJ studio, all those knobs and stuff, was that technology the same as this?
Well, the technology that they use to do that is still in use today. I don't know how many times you watch somebody that does all of that, and they do the scratching with the record and stuff like that, and they move the dials up and down to get a really good sound on it. So that is technology that's still used today. Only today we also use computers attached to them to get the best sound that you want. And instead of playing a record and having to fool with the record, you play a CD or an iPod. Does that make sense?
Yeah.
Okay. So yes, just about every electronic device we own today takes that digital signal, converts it to analog, or takes an analog signal and is able to convert it to a digital format. If you've ever blown a picture up real big on a camera, does the picture change a little bit?
Yes, ma'am.
It becomes very grainy, right? Why does it become grainy? Well, that's because you've taken something that is digital and you converted it into something that is a compound digital. Trying to think about how to say this exactly. My brain's not reaching for it right now. Essentially, what you're able to do with that, as far as when you blow up the picture, is you're seeing the different pixelations that the phone or computer or what have you had to run it through in order for it to be able to make that picture into something it could capture. Does that make sense? In other words, it could not capture that picture without digitizing it, I guess you could say. So this is all stuff that's digital. This responds in one and thinks in ones and zeros. This stuff is all analog. Why is it analog? Well, everything varies, right? A clock is analog. Your speedometer is analog. This is all stuff that's analog because it helps pick up different things. Excuse me. Okay. So number systems. This is a writing system to express numbers. So what they are using is some sort of digits or symbols in a constant manner that is understood to be what they are. If that makes any sense. Essentially what you're looking at with a number system is just like writing systems, right? So with any kind of writing system, I don't know how many of you actually have ever picked up writing in something like Egyptian hieroglyphs. All you've done with a writing system is use symbols to convey some part of information, right?
So it's like like on National Geographic, the scientists be sitting in the lab studying earthquakes. Is that like analog or something like that?
Yes. Considering the fact that the earth can pitch, roll, and yaw under somebody or under a building and bring it down, you're exactly right. That is an analog signal. So we assign values to it. So speaking of earthquakes, how do we measure an earthquake? How do we measure the damage an earthquake does? What kind of scale do we use? Or does anybody even know what that's called?
I know that animals is sensitive.
Like the EMF.
It's actually put on what's called the Richter scale. And that is how much is the earth moving and how much is it shaking, so that that's how they quantify the strength of an earthquake, is on what's called the Richter scale. Anybody ever heard that term?
Yes, ma'am.
Okay. That's not really even a thing if you don't understand it. But it's a way scientists use to quantify the movement of the earth so that they can relay that information to other colleagues. Does that make sense? It's a way for one scientist that's studying this to go, hey, Jim, we just had a 9.2 in Alaska. Well, hey, Joe, we just had a 2.0 in Alabama. Which, believe it or not, we do get earthquakes here in Alabama. We just never feel them. They're too small to be felt. But for the most part, it's a way of being able to get ideas across. Does that make sense? So technically we'll come back to that later. So we use exponents to represent values, especially in what?
Math.
Well, in mathematics for sure. But in the mathematics we use in our field, this is what we use. We use exponents to represent larger values or smaller values in ways that allow our brains to wrap around them a little more easily, right? So technically, how to say this? I'm literally trying to reach for words right now. So the way we set things up is, let's say we're looking at a kiloohm, 1,000 ohms. We use our ability to quantify things as a way of giving us the ability to understand how it works and what it is in a way we can communicate with somebody else. Okay? So we are able to almost rewrite the value of it so that we can convey it more easily to our peers. Does that make sense? Didn't mean to go completely philosophical on y'all, but there it is. So we have our decimal. So this is what we're used to because this is what everything in our world is based off of, yes?
Yes, ma'am.
Our money, how we deal with time, how we deal with everything we do is based on the decimal system. However, binary is what everything else that is electronic uses. And that binary actually can roll over into things like octal and hexadecimal. Which, like I said, we'll kind of be getting into that here in a minute. But have any of y'all ever heard of octal, binary, or hexadecimal?
Yes, ma'am.
Yes, ma'am.
Okay. So technically, if you really and truly think about it, with numbers, even in decimal format, they don't really mean anything unless we give them what? Unless we give them a weight, unless we give them a reason to be. So let's say you go back to, we'll go back as far as the Roman times. Okay? Decimal numbers would have no meaning whatsoever to them, would they? The way we write our decimal numbers would have no meaning for them because they don't give it the weight we do. Does that make sense to everybody? So the base is established by the number of digits available in the system and the position where it's set in that number. So I don't know if you remember going back to when you first started learning your numbers and you learned, well, we have the ones place, we have the tens place, we have the hundreds place, the thousands, the 10,000s, the 100,000s, so forth and so on, yes? Everybody remembers that?
Yes, ma'am.
We learned in school how to give these things the weight we give them. Because that is how our society has worked, is here's these numbers, this is what they mean as the weight and how they work. Right? So just to kind of put all that in perspective for you. So decimal numbering system, it has a base of 10. The least significant position is on the right. The more significant position is on the left. And it always moves in that factor of 10. which is nice because that's how we have learned it, right? Again, you end up with the, well, this is a ones place, this is the tens, this is the hundreds, so on and so forth. Okay. So looking at binary, okay? Binary is not the same thing as, let's see if I can put it a different way. Binary is decimal, but it's written in a different way. Okay, binary is written in just a different way. So when moving from binary to decimal, we add the digit to the weight factor. And then we have, for digital decimal to binary, we have successive division and successive subtraction. So looking at something like this is counting in binary. So for our decimal equivalents, again, we go back to, we as human beings are the ones that put weight behind these numbers. We made them mean something, yeah? Okay, so looking at binary, well, 0 still means 0, 1 still means 1, but then we start going to 2. It becomes a 0, 1. I'm sorry, a 1, 0. 3 is a 1, 1. 1, 0, 0 is 4, so on and so forth. This is what allows us to give binary numbers weight to them. Is how many ones and zeros in what combination allow us to get to this specific number. Does that make a little more sense, guys? So we're looking at 47, we're looking at something like 45. 101, 101. So that ends up equaling 45. If you notice, it starts patterning itself out. So after we get past 100 to 101 to 110, 111, I'm not saying those are actually the values of that, just easier for me to say it instead of 111. So then you got 1 with 3 zeros that equals to 8. Now look at something kind of interesting. 2 had only 1 0 behind it. All right, 4 had 2 zeros. Double 4 to 8, got 3 zeros. 16 has 4. If we go down to 32, you have 5 zeros. Might just be an easy way to keep track of binary for you. Does all that make a little more sense now?
Yeah.
So bit, byte, and word. Okay, so a bit is a single binary digit. That's going to be a 1 or a 0. Okay. So if we go back here, these two rows are the bit. A byte, I'm sorry. So a bit is a single digit. A nibble is 4 binary bits. Okay. So what do we mean by a binary bit? Well, that means that we're going to have 4 a grouping of 4 1s and 0s in some combination. Okay? Does that all made sense so far? Okay, so then we have what's called a byte. A byte is 8 binary bits. And then after you have a byte, you have a word. This is a group of 16 binary bits. And so on and so forth. Okay? So this all kind of makes sense to y'all? Now, what do you notice that it's doing? Is it's moving in multiples of what?
Doubles.
Moving exactly, it moves in doubles. So you go from 4 to 8, 8 to 16, 16 to 32, 32 to 64. That's because we tend to group these in groups of 4, excuse me. We tend to group in groups of 4. Okay. Octal numbering systems. So this allows digits to run between 0 to 7 with a weighting factor of 8. Again, this goes back to what I've been talking about this whole time. It only has weights that we allow them to have. So we can take octal and convert binary to octal by grouping them in groups of 3 to get the octal equivalent. Okay. If you're moving from octal to decimal, you have to multiply by the weighting factors. If you're moving from decimal to octal, you have to do division to get there. Okay. So then the next thing we have are what are called hexadecimal systems, which have 16 digits. Now, the real difference here is the fact that we have a base of 16. We have the ability to run through 16 different digits. So that means that we can run 0 through 9, but those are the numbers we always use. To finish out that 16 base, we had there are 6 letters added to the back of it to allow it to extend further without reusing the same numbers. Okay. So we have 2 hex digits that are used to represent 8 binary bits. And here we go for table 3. So decimal versions. So decimal to binary. Again, just kind of checking out where exactly my 1s and 0s fall in. If I look from my binary to my hexadecimal, so what is the correlation here, guys? I guess it should be something I ask y'all. What is the correlation you see? So with binary, from decimal into binary, you're just moving that 1 around and moving it different places and adding them in and pulling them out, depending upon where in the binary run you're at. With hexadecimal, it runs all the way up to 16 before it starts over and starts working a different way. Does everybody kind of see that?
Yes, ma'am.
Okay. Any questions so far on this, guys? Or any questions so far, period? Okay. So going from binary to hexadecimal, you group the binary in groups of 4 and have the equivalent hex digit. To move it to decimal, you have to deal with the weighting factors. So looking at this particular table right here, if I'm moving from decimal to binary, I just have to track how many times I have to work with that 1 to move it into place, or move the zeros back into the place they were. From binary to hexadecimal, once it gets to 15, which is the letter F, 16 means that we go to another 0, but we put a 1 out here. Okay. So this is dealing with a space shuttle console. Okay. What do you notice about this? It's different from a basic numeric keypad. It's got the numbers and letters. So these work in what? Which are the 3 that we've been talking about? I guess it might be 4.
Hex.
You're working in hexadecimal. Okay, so you have 0 through 9, and then you have the leftover 6. So BCD, or binary coded decimal system, is not a numbering system. Each of the 10 decimal digits that we use in our day-to-day life has a 4-bit binary code. We've seen it several times since I keep going back to that table. So anytime you press a number on the numeric keypad on your computer, this is what is getting sent to your computer. Is this notice saying, hey, they pressed the 1 key. Hey, they pressed the 9 key. They pressed the 0 key. That's how the keyboard talks to the computer itself. What the computer then has to do is say, okay, so you typed in 1, 5. You typed in 15. So you have typed in the digit for 10. I'm sorry, the digit for 1, and then you would have given it the digit for 5 in the binary version of it. If that makes any sense at all. Okay. So basically the computer converts the signal you give it by pressing the number on the keypad into that binary code and it has to translate from the binary code into a digital format so that it can display it on the screen. Does that make a little more sense? So here's all the different number systems we have. So looking at the number 15, well, in binary, it's got 4 ones to it. If I go to 16, I got 1 with 4 zeros behind it. But looking at the binary code, you have 1, you have the symbol for what? If you're looking at 15, you're looking at 101. Hey, look, 5 is a 101. I'm sorry, 010, 1. Okay, so binary code is looking at each number individually. Binary itself looks at how the number grows in the binary run. With octal, everything moves in groups of 7 or 8 actually, and then in hexadecimal it runs in groups of 16 before it starts over. Is all this kind of making a little sense to y'all?
Yes.
Okay. Y'all need me to clarify any more? Or y'all pretty much good with it? Okay. So codes are a system of words, letters, figures, or other symbols that are substituted for other words, letters, etc. So going back to ancient languages, things like hieroglyphics, I'm pretty sure that the Egyptians spoke to each other on a day-to-day basis. So they would not have used hieroglyphs to communicate directly. However, whenever they had to write things out and be able to be understood by their fellow Egyptian, or had to put down records of things, that's where they would have used the code that is the Egyptian hieroglyphs. Does that make sense to everybody?
Yes.
So I don't know how many of you have ever heard about the wind talkers, or how they brought in people of the Navajo Native American nation in order to help them break the code the Germans were using to communicate in World War II. Same kind of thing. It's all a code. It's not so much, you've created a separate language using that code, and being able to convey that same language with a code is how we allow for different kinds of communication. Okay? So I don't know how many of you have ever played Spy Master with your friends or with your family and done well, here's this book, here's this way I've written out this code, so here you go figure out what I'm trying to tell you. I know people used to play that a lot as kids, and it's something that can still be played today. But what you're doing is you're substituting different words or letters so that you can be understood by one person, but maybe not another. Again, that's just kind of what codes are. So acronyms. So what does CIA stand for? When you're using acronyms, what does CIA stand for? I'm sorry, Mr. Addison, I can't hear you. I think your mic's not working right, Mr. Addison, because I can't really hear you very well. Okay, so it does mean Central Intelligence Agency. Yes, you're correct. It's kind of like FBI, Federal Bureau of Investigations. We use acronyms so that it's got its own meaning. And all that really is just to keep it from becoming an overly lengthy word, because you don't want to sit there and say, I'm from the Federal Bureau of Investigations. Well, yeah, by the time you've rattled that off, the bad guy might be gone. Whereas if you use the acronym FBI, you might still be able to catch them. And then we have what's called the ASCII, which is the American Standard Code for Information Interchange. And that's what is typically used by computers and the internet to convey that information. All right, so the ASCII code, it's been around for a while, ever since computers really. It's what we use to represent the alphanumeric data, and uses 7 bits. There's 128 different code combinations as to what is used on your computer. So, taking a look at this, we have what? We have acknowledge, backspace. So if you look at the BS, backspace, so this is how they do the information change here. So it has a 3-digit code for one part of it, and then it has a 4-digit code for the rest of it. You'll all see that pretty well? So for, let's say, delete, the first part of the code is 001, okay? And then it goes to 4 zeros after it. So if you're doing, let's say, the letter A, that's 100 and then 0001. So this is how they figured out how to take a keyboard and be able to create information on a computer with it. Because every time you hit a keystroke on your keyboard, I don't care what exactly you're hitting, I'm sorry, DLE is a data link escape. I don't know if I've ever really seen that one on the computer, but anyway. Getting out of my out of this, but anyway. So each and everything on your computer keyboard, so all keys and every subkey, they have a way of creating that database so that it makes everything usable in a way that works for everything. Okay? Does that make sense to everybody? So your computer does not actually read letters. What it reads is the code for the letter and translates that into a document. Make sense to everybody at all? Kinda, sorta?
Yes, ma'am.
Okay. So you have your vertical tab and your horizontal tab. For your horizontal tab, that's HT. So looking here, we have 3 zeros to begin with, and then we have 1001 I'm sorry. Yeah, horizontal tab is 1001. What's another one we typically use a lot of? Well, we use spacebar for sure. That's SP, right? So every time you hit your spacebar, trying to find the right one here. It's not listed. I said everything that you press on your keyboard should have some correlating bit here. Oh, here's space. So if you hit the space bar, what you're actually sending a code for is, the code you're actually sending is 010 and then 4 zeros for the second part of the code, saying, okay, we hit the space bar. And that's what your computer translates it as. So if you were to write your name in ASCII text, so for my, or if you were just to do your initials, right? Wouldn't be that hard. So for the first one, you have A for Allison, so that'd be 1000001. If I did my last initial, 100, and then 0010. This is all the capital letters, and then they also have all the lowercase letters. So this was done by Rich Raymond using his name. So R, you have that 1010010. So if you go back here, I should be able to find R right here. So that's how the computer translates it. That's what allows it to write your name. And your computer I hate to say computes it. So what your computer does is it takes this code, it breaks it down real fast, and is able to push it back to you on a Word document and say, this is what you typed. Does this make sense pretty well? All right, so if we were to do the this phrase into ASCII 2, so looking at this right here, so I'm trying to make sure I do this right with you. So the phrase is, now is the time. So now starts with a capital N. Well, look, here's our capital N. It's a 4E. If I look for that lowercase o, it's a 6F. So let's see if that's correct here. 4E, 6F. And then we would just continue. You have 7, 7, 7 right here for the W. You would have a space, which would be a 2, 0. Then you would have is, which is using a lowercase I. So that's 6, 9. Now, can I see where I'm going with this? Again, this is how your computer would break this down. It literally breaks it down into this kind of a code right here, saying, okay, so on this piece, this is this, this is this, this is this, so on and so forth. Any questions so far, guys? Any questions on this? And how it relates to the tables we've already seen? So we have what's called a Unicode. This is the standard for consistent encoding, representation, and handling of text used in most of the world's writing system. There's 135 modern and historic scripts and symbols. So basically, when you go to Microsoft Office and you open that up, they use a Unicode to encode and represent the writing systems from all over the world. So let's say you speak Spanish and you need to write a letter in Spanish. Well, this code would help you do so. All the different fonts and stuff, this is what breaks that down for you. Let's see if this will pull up for me. So if you were to look at, excuse me, so this goes back to your keyboard. So looking at this, escape 7-6, these are the codes that when you press this keyboard, creates the communication between the keyboard and the computer screen and the computer monitor, saying, hey, these are the buttons pressed, this is the order it's pressed, put this on screen. Display this for the person doing this. Now, what's really kind of cool that you can't really do so much with Windows 10, I think it's a little harder to hack into the back of it, is that you used to be able to go to certain screens and go in and change things about the codes and stuff that are on your computer. I don't think you can do that with Windows 10. I think they've kind of locked that option out. But used to, you would be able to tell it that, you know, every time you pressed, let's say, 4C, that instead you meant to press 4A, and 4A could become 4C. You used to be able to go in and change those codes. You can't really do that much anymore, simply because Windows kind of locked everybody out of doing that. I'm thinking it's because too many people had issues going in, doing something like that, and forgetting they did it. So the next time somebody comes along behind them, they start trying to use that key, and it's not putting out the right code. Actually is something that used to happen quite frequently. So numerical quantities occur in analog form but are converted to digital for computer or digital circuitry. God, I can't talk. The binary numbering system is used in digital systems because the ones and zeros are easily represented by on-off transistors. Their output voltages range from 0 to 5 volts. So if you get 0 volts, you have 0. If you have 5 volts, it creates your 1. Every numbering system can be converted to decimal by multiplying each digit by its weighting factor. So binary numbers can be converted to octal by forming groups of 3 bits, hexadecimal by 4 bits. So we can convert from decimal to binary, octal, or hexadecimal The binary coded decimal system uses groups of 4 bits to drive decimal displays, such as those in a calculator or on your computer. Okay. Any questions about any of that, guys?